the equipments working in the system based on their terminal voltage have their plus or minus range of tolerance. Beyond that range, definitely equipments are sure to perform wrong or malfunction. Suppose they were the measuring instrument, if you hope so, those instruments are sure to measure or pick up wrong data or erroneous data, which will be used in the computation of your desired control action. It will lead to or it will cause erroneous results and cause wrong action. Further, it will cause a disturbance or spoil the system, the healthiness itself. Therefore, working with the specific voltage and within the permissible range or limit is very necessary. Hence, voltage control is very necessary. Basically, voltage control is done through AVR, automatic voltage regulator control loop, situated around the generator has to do it. But due to the various facts on which voltage is dependent, it need to be controlled from different ends itself. Therefore, the delivery of power from generating station to the receiving station over the transmission line mode, it again adds up reactance to the system, inductiveness to the system, additional drop in the system, which definitely cause a system to become more sluggish and inferior in that perspective. Therefore, the voltage profile definitely get affected. In this view, we learned that there is a direct dependency or stronger interdependency of active power with the frequency and reactive power with the voltage in a power system. That is one indicator enhances our need. If the voltage of the system is not becoming stable or it is oscillating, flicker, such observation if we find on the power system operational aspects, definitely it is an indicator that there is a need for reactive power that is not addressed or fulfilled right now or unable to make it fulfilled would be a outcome of that. Therefore, in that perspective, there are different identifications. With those different identification, different methods are incorporated to fulfill that required reactive power substitute to the system so that system voltage become better and as required within the range permissible. The first and foremost mechanism is line reactance compensators. As we are very sure, power system is a various incorporates various types of generator, transmission mechanism, transformers, switch gears and loads. Definitely to deliver the power to the end user, transmission mechanism, cables, etc. are very necessary and essential. They being more in inductive by approach, definitely reactance cause additional burden on the system. So the reactance of the line need to be compensated. We cannot make it zero because transmission line do possess for its specific inductance and reactance per kilometer length of measure. Then how do you compensate that? You need to have reduction of its offered reactance over the length by additional compensation mechanisms. Like if we have a transmission line possessing XL as a total reactance, if you want to reduce that, if I incorporate series capacitor along with the line XC, which XL and XC get compensated such that the net reactance offered by the compensated line stand as XL minus XC. So the total reactance XL now got reduced by taking off the compensation adopted by the series capacitor. One concept what is triggered here is use of series capacitor. Capacitor in series with the line reduce the overall reactance of the line such that the more of the reactance part is eliminated and power transfer takes place very effectively. So that additional drop what would have happened due to reactance part is reduced or diminished. This way, reduction of line reactance is one method by series capacitor. Other way, there could be a shunt reactor and capacitors which act as sink or source of reactive power respectively. This can be viewed from the perspective where loads, when a large industry or a huge connected capacity load which is absorbing highly inductive power, highly lagging in power factor. Locally, lot of capacitor can be hooked across the load terminals at different terminals so that the lagging volt ampere, lagging VAR can be compensated locally by the capacitor providing leading volt amperes. By having this load side compensation adopted, you are meeting the requirement of the reactive power locally because it is very economic to compensate the reactive power at the point of need itself, as we are aware. Overall system being highly inductive, transmitting reactive power over a large distance impose lot of limitations and higher loss. Hence, larger distance over larger distance transmission of reactive power is not facilitated. It is discouraged. It is in fact to be compensated at the point of need or at the optimal point of a system, which is commensurate and can be accommodated in the system. Therefore, as and when there is a compensation due to additional load or lagging VAR by the capacitor, suddenly loads are removed. What will happen? A highly compensated system, which is with the capacitor highly acting upon the system to compensate, suddenly loads are removed, that leading VAR float on the system. That will affect the system operation as well. So therefore, the system which is delivering power to the highly inductive system which is overcompensated or compensated now become highly overcompensated if we are not going to eliminate capacitors immediately or in a systematic manner. Therefore, to compensate that, shunt reactors are preferred. It means reactor do absorb reactive power and capacitor do supplement reactive power. By compensating these with the systematic switch off and switch on by the adopt of technology, we can definitely manage the reactive power in the system. It is to highlight use of shunt capacitor and a reactor in a system in accordance to your requirement. As per the load, as per the delivery, switch on, switch off them or eliminate them in part or full according to the requirement, such that such an management also makes the requirement of reactive power in step and which in turn improve your voltage profile. That was seen by adoption of shunt reactor and capacitor. The another is rotating machine, synchronous condenser which can act as source or sink of reactive power. For this I was narrating an example, synchronous motor running with zero mechanical load. There is no load on the shaft, which is running with the free load with the control of excitation, with the highly leading and highly lagging or overcompensated or undercompensated mode of that excitation make it to supply reactive power and absorb reactive power. So this way synchronous condenser can act as a source when it is overcompensated or overexcited, and it is absorbing reactive power when it is underexcited. So this is a synchronous machine based approach which is very costliest mechanism presently. It is the oldest mechanism because it involves rotating machine absorbing power from the grid running without any load on the shaft. Only the excitation control you are managing to compensate your required reactive power of the system. Hence it is costlier, but still it is in practice. And other is regulating transformers like tap changer and booster transformer. So the ultimate aim is to see to it that voltage is maintained within the range prescribed with the working range plus or minus tolerance. Voltage need to be maintained in the system. For that, definitely a transformer based approach when we prefer tap changing facility with a transformer makes it possible, or the booster like transformer, a transformer having addition of delta V or removal of delta V from the line voltage makes the receiving end voltage shifted or reduced appropriately by the configuration. When we see the diagram, we are able to see what is that mechanism of tap changing transformer or a booster transformer in the sequences. This is also very interesting. Then we have power electronic adoption, which is fact devices, which are the custom devices definitely make use of uh, power electronic converter, inverter, topology, voltage source, current source concept, capacitor, inductor together in a systematic manner switched such that they are able to perform your required compensation as per the need. So this is a very interesting evolution from the power electronic perspective, very costlier because it involves the thyristors, IGBTs, MOSFETs and all power semiconductors which will be acting on the line, and they are very sensitive. Lot of switching effects are there, lot of compensating mechanism need to be adopted, and this is sophisticated but costlier in work. So this is how the pack devices really make the things possible. And moving to the concept, a single line or a single phase representation. One system we have shown here with a voltage source and a transmission and impedance R plus Jx, and there is a load with a voltage V, load voltage, and power absorbed by the load is active P, reactive power Q, P plus JQ, and current flowing from source to load B, I. Then how we can draw the vectorial representation of this single phase representation of the load voltage and delivery generator voltage through the impedance of the particular transmission line. You can see a vector diagram just beside. The connection, how is that generator's profile E is obtained from the receiving end profile and backward. You can see a vector OA drawn horizontally show you the terminal voltage of the load, which is V, and system is highly inductive because absorbing reactive power as well. Then you will find just behind the vector OA there is a vector current shown lagging behind it by an angle phi, which is clearly indicative that lagging system. Then if the system is having a drop I into R, I into X, they are represented at the tip of the vector V, I into R in phase with the current. In phase with the current, a vector IR is represented, and drop due to I into X. I into X is quadrature component, which is perpendicular to the current. Current is here, lateral, perpendicular to that is the current. I into X is represented. You can see this. When I take V, IR, IX, that represent the internal or the generator's voltage E. Load voltage plus the drop give you the terminal voltage of this one, which is E here. So this is what a vector diagram can be rewritten. Now you will find angle between E and V as power angle. This angle play a role, vital role here. For the transfer of power from generator to the bus, this angle play a vital role. Later, we want to study from this what is that sensitivity of voltage on reactive power and connectivity with those requirements. To understand that, before going to the next, we have to make some modifications or extended work. You will see few dotted lines. Vector OA is extended dotted forward up to C, and there is a drop of perpendicular from E downward. You can see there, just an extension. I just repeat, vector OA is produced forward, right side, dotted line, and from the E, drop a perpendicular to the OA vector, cutting it at C. Then similarly, at point IR vector tip, at the tip of the vector IR, from there, drop a perpendicular to the OA vector, cut it at B. You can see dotted line extension. Similarly, from the tip of the vector IR, draw a parallel line to the OA vector, which you will see dotted line, cutting that at E. Therefore, you can say from the vector IR tip, draw a line parallel to OA, cut the drop taken from the E to cut it at E. So this way, some extended work is performed. It is to correlate the drops due to resistive part, drop due to inductive part, and connect them to voltage and relate how is that reactive power and voltages are connected to one another. So in that perspective, these drops and these extended work represent the overall horizontal axis from the extension A, means vector V. From A there is a small length of vector B, AB. From B to C, BC. Whole A to C, if you measure, that is given as small in phase change in voltage delta V, in phase component. Then you will find vertical axis D to C, you will find this as delta VQ, phase quadrature component of the voltage. So whenever you find a load is connected to a receiving end, power is being delivered, definitely there is a drop in voltage. The mismatch of voltage delta V I am trying to speak. What is that expected voltage? What is right now the voltage which is prevailing? V minus delta V is the right now working voltage. That delta V is characterized as component of delta V in phase with the voltage and in quadrature with the voltage. I want to take what is that? That's what I am trying to say. The delta V part in phase with V is delta Vp in phase, and delta Vq is phase quadrature. This is a dotted line D to C and dotted line A to C I am trying to mention. Now my task is to compute what is delta Vp, what is delta Vq from the given terminologies and data. And for that I should remember what is this angle with the phi, it is lagging. It is a current is lagging with the V by an angle phi. This phi become an angle with respect to IR vector with the extended line. So IR is parallel with the I. There is an angle phi made by the vector IR from the horizontal line here. Then this line and this triangle E and this triangle which I am making a dotted line and moving upward, we can see this triangle. This triangle is going to have this angle D. You can see this angle is phi. This is phi, and angle over here is also phi, and angle here is also phi. So therefore with this angle I can correlate. What is that? What is that AC? What is that DC? I can connect and I can calculate, because totally I want what is delta Vp, what is delta Vq, phase component, phase quadrature component of the mismatch I want to quantify. Let us see that. I am titling it as dependence of voltage on reactive power. How is that reactive power really make voltage more sensitive on it? To understand that, I refer the same diagram. You can witness the same diagram I have picked here. From this, I will just draw an equation. What is OE square? This hypotenuse. OE square is, you can just see a triangle, right angle triangle made up of E, O and C. I can write OE square equal to OA plus AB plus BC whole square plus DC whole square. I can write it. Adjacent side is sum of some parts OA plus AB plus BC whole square plus DC square, that become OE square, nothing but E square. As we know, OA is V, AB is IR cos phi, because this angle included is phi. IR cos phi become a projection AB. IR's projection along horizontal axis is AB, that is IR cos phi, we can see here. Then what is BC? BC, this side. B to C is same as this vertex and E. Can you see this? These two are, this forms a rectangle here. This forms a rectangle. BC is parallel to another side dotted here. So I can get this side from this right angle triangle. So this right angle triangle is having at this corner an angle phi. So hypotenuse is known to me, angle is known to me. I can write this opposite side divided by hypotenuse give me sin phi. I can write Ix sin phi, nothing but this side. This is parallel to this BC, same as BC. So BC is Ix sine phi. So there is no angle mentioned here. You can just see geometry. This is an angle phi and this is an angle phi. With this angle phi, what is this angle? And 90 minus this phi, and this must be phi. So how you get it? So this is phi. Okay. This angle turns out to be 90 minus phi. 90 minus phi. This angle is 90 and this must be phi. When I make this sum of this angle, it becomes phi. So therefore, this angle phi with the sinusoid opposite side divided by hypotenuse give me BC equal to Ix sin phi. Now as you know, what is DC? DC. DC is, you can see geometrically, DE minus CE. This CE part you can cancel from the DE, I can get DC. Then what is this? DC. DC is from this triangle, adjacent side, hypotenuse. I can say Ix cos phi. DE whole length refer Ix cos phi minus CE is parallel to this line here. This line is having a small triangle here, correct? This small triangle phi, opposite side divided by hypotenuse. We can use it as IR sin phi. You can see Ix cos phi from this bigger triangle minus this small side is from inner small triangle here, IR sin phi. So I can get DC. What I got totally? I got OA, I got AB, I got BC, I got DC from the representation of this vector diagram. Then I will substitute in this E square equal to V plus IR cos phi plus Ix sin phi whole square, the first term. Substitute them in step plus DC square. What DC I got? DC is Ix cos phi minus IR sin phi. So I will be doing it. Now we know that active power and reactive power relationship with current and power factor. How we write? P is VI cos phi, Q is VI sin phi. Having this understood, let us write what is I cos phi? It is P by V. What is I sin phi? Q by V. Can you see over here some substitution terms? I cos phi, I will be replacing in this equation. I sin phi, I will be replacing in this equation by P by V, Q by V. If I do it, let's watch. E square equal to V as usual. R is here. I cos phi. What is I cos phi for me? P by V. It become RP by V. Can you see this term? RP by V, which is IR cos phi. And Ix sin phi is going to change Qx by V. You can see xq by V whole square plus the second term Ix cos phi. I cos phi nothing but P by V. It is Px by V minus IR sin phi. Q and V I'll substitute RQ by V. It means I am trying to bring in all the relevant terms: voltage, like bus voltage, generator voltage, line resistance, line reactance, active power absorbed, reactive power absorbed. All the terms we are bringing into the equation. Then we are going to separate it such that what is that dependency of voltage on reactive power can be witnessed. Let's see. It is written as V plus this term RP by V plus XQ by V is written as in phase component of the deviation delta Vp plus this whole term is written as delta Vq. So we got now V plus delta Vp whole square plus delta Vq whole square. This differential term is called phase in phase deviation, is phase quadrature deviation voltage. Therefore, it is separate term. Delta Vp is in phase with V. Delta Vq is in quadrature with V, which you can see here. So I am speaking about Rp by V plus Xq by V. This is delta Vp, which is this term. The term which is marked here by arrows. Whole length A to C. A to C is delta Vp. This is V plus delta Vp, you can see whole square, plus delta Vq, this term which is given as Xp minus Rq divided by V, and invariably I got back the same thing. Therefore, E square equal to V plus delta Vp whole square plus delta Vq whole square. I am trying to get the supply voltage, generator voltage is equal to the load voltage V plus quadrature in phase drop square plus quadrature drop square as my E square term. Let us see how it can be still simplified. If there is a notice, if delta Vq is very smaller than V plus delta Vp. Let us look into this. What is this? This term, I am speaking, this term, the second term is very smaller than this term. This term. It means this term we are comparing with another term. What is that? If delta Vq is very smaller than V plus delta Vp, or P into X term is very smaller than V square plus Qx, then what will happen? The term we can write here, E square equal to V plus Rp plus Xq squared by V, or second term I am taking off, which can be written as, you can see here, square and square I remove, what remains is E equal to V plus Rp plus Xq by V. The square and square I cancel. This V I transfer to the LHS side. What will happen? E minus V equivalent, very closely equivalent to Rp plus Xq by V, which itself is delta Vp. I mean, this term is substituted for what? Delta Vp. When I take this V other side, E minus V is called drop or fall in voltage or change in voltage. Difference in voltage is nothing but delta Vp. When we consider the quadrature component is very negligible at that time, the drop in voltage is only due to in phase component only. So thus the arithmetic difference between the voltage E and V is approximately equal to Rp plus Xq by V. So this very interesting formula which we will be using in solving the numerical problem. Further, if the transmission line is assumed to be highly inductive, resistance is very negligible. When R goes 0 in this term, what you can say? The first term goes 0, Rp goes 0. What remains is Xq by V equal to E minus V. You can see here, E minus V is Xq by V. And this is one term we can see. When the line is highly inductive, resistance is negligible, the drop or change in terminal voltage E minus V can be given as Xq by V. Now, this delta Vq which we consider, which really affect the angle delta, which is, you can see this delta is equal to inverse sine of delta Vq by E. What is this? Sine function, sine delta. I just go back here. What is sine delta from this? Sine delta is opposite side, delta Vq, okay, divided by hypotenuse, OE nothing but E. Delta Vq by E is sine delta. The same thing is done here. So delta Vq affects the angle delta, that is delta is inverse, sine inverse delta Vq by E, and depends only on P. What is this exact delta? Power angle. This depends on P. So therefore, under short circuit condition, on a complex power, when I represent SC, how it can be written then? On a short circuit complex power, EI conjugate. The conjugate, when I take a current during the short circuit representation, it become V into ISC conjugate, or when I represent this by impedance format, V square by ZC at conjugate. So therefore, if I neglect the resistance part of the impedance, then it become short circuit complex power. The complex power during the short circuit is square of the voltage divided by X. I would say it is inversely proportional to system reactance. When I maintain whatever the voltage V, so 1 by X, complex power is inversely proportional to reactance. So larger the reactance, lower the complex power. Lower the reactance, higher the complex power. So therefore, this one term identify how is that the in quadrature V delta VQ cause change in delta, how delta is dependent on active power during the short circuit, how complex power is connected to reactive power can be seen from this. So this equation it will be using, this equation V square by x somewhere in the numericals will be using, and E minus V equal to x cube by V, this equation also will be using, and Rp plus x cube by V, this equation also will be using in the numerical. So this will be, these are the equation which will be using in the equations. So what we got from this is the sensitivity of the voltage on the reactive power. So rise or fall in voltage dependent on reactive power Q, reactance divided by system voltage x Q by V. This is how for the line neglected with the resistance, the line having resistance Rp plus x Q by V. So therefore, the difference in or drop in voltage, change in voltage is directly connected to Rp plus x Q by V. So if I view still further as a sensitivity of the voltage to the change in P and Q, naturally when a system is in operation, to deliver active and reactive power from the operational perspective of the power system, due to the dynamic changes in the load, definitely P and Q need to be addressed by the generating system. Then how is that voltage getting an impact of that? Then we have a very specific representation, which is mathematically we have voltage at any bus or a node is defined by a function of P and Q, which is given as V equal to, or V is a function of P and Q. So therefore, for a small change in V, which can be given as dV, dV differential voltage, dV is partial differentiation of PQ with respect to representation. What is that? Dou V by dou P. Partial differentiation of this V equation with respect to P at discrete dP, and partial differentiation of above equation with Q at discrete dQ, which give me dV. This dV nothing but E minus V, what we have just got here. Change in voltage, E minus V is nothing but dV, small change in voltage. Similarly, we are trying to get that sensitiveness in terms of P and Q by this way. Defining voltage of a bus or a node is a function of P and Q. For a small change in voltage V, it can be quantified as dV equal to partial differential of this equation, dou V by dou P at dP, dou V by dou Q with dQ as a discrete. Now by differentiation terms, dou P by dou V can be written as adjustment, dou V by dou P, by cancelling mathematically it become 1. What I am doing, I am trying to manipulate the terms over here to represent in a standard format. Therefore, we know dou P by dou V is dou V by dou P, when I cancel it become 1. Similarly, dou Q by dou V into dou V by dou Q equal to 1. By making use of these things and representation over here, you can see here. So I try to write this equation as dP over dou V in the denominator. How I did it? You can see dP as it is, dou V I took the denominator and make it the denominator of that, dou P by dou V. Can you see this? Similarly, plus dQ by dou Q by dou V. This way, I can rearrange this equation, and using the above consideration, which is that delta V or a small change in voltage is E minus V, which can be rewritten from the previous equation which we have here. This equation, here we have E minus V equal to Rp plus x cube by V from this equation. Can you see here? E minus V into V minus Rp minus x2 equal to 0. You can just see the same equation. This equation, E minus V, are you sure? E minus V into V, okay, equal to Rp plus x cube. I can take everything on one side and make it 0. That's what is being done. E minus V into V minus RP minus XQ equal to 0. That's what is being written here. E minus V into V minus RP minus XQ equal to 0. Here E is the sending end voltage and V is the receiving end voltage, which we have seen. A system, E is the sending end voltage, V is the receiving end voltage for a system with a transmission mechanism. The same thing we are viewing here. Dou P by dou V, I can write here. Dou P by dou V equal to, I can differentiate this equation. If I differentiate this equation as dou P by dou V, I will be getting E minus 2V divided by R. It means what I would have done is this, make this equation such that I will be able to differentiate dou P by dou V. Keep this here or keep this only here, rest other side. I will be getting E into V, EV minus V into V, V square. This is the first term, minus RP minus XQ. When I take this differentiation like this way, dou P by dou V, if I differentiate, I will be getting E into V as E minus V square. When I differentiate, it become 2V, and from this I will be getting only R. So I push at the denominator. I will be getting from this equation, when I take dou P by dou V, I will be able to get E minus 2V by R. Similarly, when I take this equation dou Q by dou V, when I take differentiation of this with the perspective of V with Q, so E minus 2V by X from this equation only. And these two terms, dou P over dou V, dou Q over dou V, you can watch it the denominator. Here I find them. Dou P by dou V, dou Q by dou V. From these I place them here. So you will find dV equal to dP divided by E minus 2V by R, dQ divided by E minus 2V by X. If I rearrange it, so take this R to the numerator, take this X to the numerator, it becomes dP into R plus dQ into X divided by E minus 2V, because E minus 2V is common both sides. I can make it as a common. I will be getting dP into R plus dQ into X divided by E minus V stand as small change in voltage. I am trying to bring a sensitiveness of voltage on reactive power. A small change in voltage dV is written as dP into R plus dQ into X over E minus 2V. For a constant V, let's say delivery of voltage is very constant and delta V are negligible. At that time I can say this term, when dV goes 0, I can surely write dP into R plus dQ into X divided by E minus 2V. So E is almost equal to V. When a constant voltage is experienced, then E is always or very close to V, then this term cancels with one E only. So if I correlate it, I will be getting dQ. What is this dQ? dQ is R by X into dP only. It means for a constant voltage delivery, I can get dP into R plus dQ into X over E minus 2V on representation as what is dQ. dQ is when I transfer minus R by X into dP. That's all. Then I can make similarly dou Q by dou V, dependence of reactive power and voltage as E by X. So therefore, this is how the sensitivity of voltage on active and reactive power can be represented by this way, and we can stand as a small change in voltage is dP into R plus dQ into X over E minus 2V, and for a constant V and delta V, we get what is dQ in terms of dP and R by X. Later, if we extend, what is that voltage prevail? Suppose you have a generator absorbing reactive power and delivering reactive power. What is that mismatch? What is that impact of that on that generator? We can see from this curve. So that generator with a voltage axis, vertically central, and its reactive power abilities, generation, absorption, and a slope of its operation we can see. So therefore, whenever there is an absorption of reactive power, and there will be a dip in voltage. So when the system absorbs, so generator need to feel deficit of this particular voltage. So when it generates, there is a superior voltage you get. So that depends on this equation. So this is the sensitivity of voltage on reactive power can be seen from this. This is another way of looking. This is one equation, one type of derivation, dependence of voltage on reactive power. This is sensitivity of voltage to the changes in P and Q. This is the second derivation one need to get into. Similarly, we have interconnected systems. When we have two systems interconnected, how do this reactive power comes into picture, play its role? You can see two systems interconnected. A system with a generator and transformer at bus 1 and a load. A system with the generator 2 transformer at bus 2 by a impedance or reactance of the line Jx, which you can see here the representation. Terminal voltages of the buses are respectively V1, V2. Power which is flowing from 1 to 2 and other side marked on the system as P1 plus JQ1, P2 plus JQ2. From this perspective, let's see what happens. If reactance of the line is very larger than resistance of the line, the transmission mechanism with which it is interconnected, if reactance of the transmission line is very greater than resistance of that, then reactive power, whatever is flowing, is determined by delta V. So therefore, what is that really flowing, which is nothing but what is that drop experienced. So from vector diagram, we can come to know the terminal voltage of bus 1, if assume that power flow occur from bus 1 towards bus 2, definitely bus 1 must be leading with respect to bus 2. If I say an angle delta 1 concerned to bus 1, delta 2 concerned to bus 2, delta 1 must be leading with respect to delta 2, then only power flow can occur from bus 1 to bus 2, assuming V1 is larger than V2 by magnitude in that direction. Definitely I will find representation of voltage V1 from V2 perspective. From receiving end perspective, what is that sending end voltage V1? I can conclude it by a small vector diagram, drawing it as, you can see a horizontal line, a vector drawn representing you V2, vector V2, and the current what is flowing in the system is highly inductive because of inductance. Let I be following the vector V2 behind by an angle phi, some angle, which is I shown here. You can see I is behind the vector V2. Definitely, if the system resistance is 0, as you have mentioned, highly inductive, resistance is 0, the drop due to I into X. I into X is perpendicular to I vector. You can see this. Perpendicular to this axis, I into X is drawn at the tip of V2. Then that, if I join with the origin, that result me total voltage profile of the V1. V1 is V2 plus I into X vectorially. That means V2 I must know, I into X perpendicular to the I at the tip of this V2, if I join, that become V1 for me. This is the first type of work. Later, let us identify quadrature and direct axis components of current and reactances. How to do it? Look into the I. Current I is lagging behind the voltage by an angle, and make its component, the component of this in line with the V1. Can you see this? I in line with this, a drop of this, a drop a perpendicular to this, perpendicular from this to V1, you will find ID. ID is a vector along the voltage V1, which we call as ID, component direct axis component of main current in the voltage axis. So it is ID. Then from this, if I take a joining vector, this become VQ or IQ, which is nothing but quadrature axis in perpendicular to ID. If you draw a vector here and join it, that become a resultant I. I am going reverse. I am trying to get from the resultant current I, what are all its two component, one along the voltage, one across the voltage, which is, if I take ID as the in phase component of I in line with V1, another must be perpendicular to that. That is called dotted line. I would have drawn here, it is shown here also. Both are same, parallel to each other. So ID is the direct axis component of main current I, and IQ is quadrature axis component of main current I. So I could get ID, IQ. Now from this particular I into X, I have an option. I into X is the total inductive drop. Out of the total inductive drop, this is the resultant. What is that? Drop due to current IQ, drop due to ID, I can correlate here. To get that, let's see, ID into X if I take. ID is in this plane, ID into X is perpendicular to this, there is a line drawn from V2 dotted, which will touch the V1. And IQ is exactly perpendicular to V1 and make a line perpendicular to this dotted line, which is in line, which you can see IQ into X. I mean to say ID into X is perpendicular to ID. IQ into X is perpendicular to IQ, which you can see ID nothing but axis of V1, same as this line. Okay. Then perpendicular to that, you have to join a line to V2. Then IQ is dotted here, and IQ into X is perpendicular to this nothing but axis along the V. So if I join these two vectorially, that represent I into X. What I am doing? I am going reverse. I current into X, Ix. Its real component, one is ID into X, another is IQ into X. For this, if you recall back, power angle curves of a synchronous machine, one experiment we have done. So that kind of revoke, if you see, probably you are able to distinguish what is direct axis component of the main current, quadrature axis component of the main current, and drop due to direct axis component and drop due to quadrature axis component we can get back. That's what we are trying to do here. I am trying to distinguish this I into X into quadrature component and direct axis component and get the value of V. So therefore, what exactly shows, when V1 is leading with respect to V2, there is a flow of power from 1 to 2. Other way, if V2 is leading with respect to V1, power flow occur from bus 2 towards bus 1. You can see a small vector diagram, V2 vertically shown here. V2 is vertically shown and V1 is just drop. So it is V2 minus I into X. V2 minus I into X is V1. And behind that we have I here. It means power flow can occur in an interconnected system from bus 1 to bus 2 or bus 2 to bus 1, depending upon the leading and rising edges of the voltage. So therefore, likewise, the delta of the system matter here. This delta matter. This is called power angle. You can see this delta. Delta is the angle between V1 and V2. So this defines how is that power flow occurring. So therefore, interconnected system, when power flow is noticed among the controller, excitation control from the generator perspective makes it possible whether to deliver or whether to absorb. We can see here, see like IQ, the component of current in quadrature to V depends mainly on V1 and V2 difference. Then hence Q depends on voltage difference. Reactive power, what is exchanging among these interconnected systems, highly depends on voltage difference. So this is what sensitiveness of the voltage we have seen here. Delta V. Delta V is E minus V between two buses. That is again connected to reactive power only. The same way we have here. Q depends on voltage difference. If we now vary the generator excitation such that bus 2 voltage is larger than V1, then direction of reactive power flow is reversed. I mean, we are worried about reactive power here. How is that reactive power flow occur from bus 1 towards bus 2? When is that? And bus 2 towards bus 1? When is that? So that's what excitation control is such that V2 is dominating over V1, then direction of the reactive power is reversed. So the direction of active power can be controlled adjusting the prime mover. This is very interesting. When we see P balance is adjusted by mechanical supplement of turbine, which will enhance its mechanical power so that electrical need is worked out. So P is addressed by prime mover, and the direction of the reactive power flow can be controlled by adjusting the excitation of the generator. So see here, ALFC, AVR are coming over here. For the control of active power, ALFC come into picture. So ALFC will look forward with respect to the active power supplement by making mechanical supplement to the turbine. And to control the direction of flow of reactive power, AVR comes into picture. That AVR look for excitation control of the generator. Therefore, both the control loops in the generating system are very interesting and they are independent and they are interconnected such that there should be a P balance and there should be a Q balance side by side. So they have to be systematically organized by the AGC. So therefore, interconnected system, a short view how reactive power flow among them occur can be seen by simple block diagram having viewed it. Then we have seen that the scalar voltage difference, a small one more line of paragraph is here. The difference in voltage between two nodes is given by delta V equal to Rp plus Xq by V, which can be written if you make Q equal to 0, where is that? Here, Q equal to 0, reactive power equal to 0, then there will be no voltage drop between bus 1 and 2. It means it is a situation if we make Q equal to 0, reactive power absorption itself 0, definitely reactive power is the culprit, is a cause for change in voltage. If you make it 0, no more drop in voltage between bus and 2. We can write the equations of the receiving end power simply Q2 equal to K minus R by X into P2. So it is nothing but transformation ratio of the transformer minus R by X into P2. So it means to say if we need to hold V2 constant by varying P2, Q2 as given by the equations, P must be supplied. It means we have to maintain V2 constant means P2, Q2 I have to properly inject. So therefore, if the amount of Q2 cannot be supplied, then V2 cannot be held constant. It is nothing but when we want to maintain V2 constant with varying P2, definitely when V2 need to be held constant, reactive power has to be fulfilled. Then P can be varying, P can be drawn, active power can be varied, and voltage we need to keep constant means reactive power has to be maintained appropriate. If we are not able to fulfill Q injections properly, it indicates that V2 you cannot maintain. So therefore, if P2 changes by an amount of delta P2, then delta Q2 what is going to change is R by X into delta P2. Now there is an indirect link. P changes, it affects Q also. That's what I want to convey. So therefore, it is not only the Q requirement cause the voltage change. Q requirement will change because of P requirement also. And Q requirement will make an eye on V. If we are not able to supply Q properly, V you cannot maintain. If we cannot maintain V properly, P we cannot maintain constant, because we know between two buses, active power delivery P12 is V1 V2 divided by X sin delta 12. There comes a voltage. If Q cannot be maintained, that is because of V. If V cannot be maintained, P get affected. If P get affected, Q get affected in this way. So there is a triangular connectivity between reactive power with the voltage, voltage with the voltage on active power. So active power